All right, so Nicole will start us off. How do you add extra carbons to a product? Good question. So for example, here you have an example of extra carbons being added to the product. I'll also jump down to the synthesis. Whoa, what happened here? Let me back up to the top. Okay. If we go back to down to the synthesis sections here, there are several examples where you can see carbon being added in different ways. So like here, here, here. So a few of them. So let's take a look at that. How do we add carbons to a couple pages? So this is actually kind of a little too general. Let's be a little bit more specific. We're talking here about forming carbon-carbon bonds because adding carbon like as a other nucleophile or something, you can do that too. But when you actually want to connect a carbon to another carbon, that's a very specific thing. There's only a couple ways really that we've talked about doing that. So first, let's just go chronologically from class here. The first way that we did this was using acetylide ions. So that you can take sp hybridized carbons with a hydrogen, so a terminal alkyne, and that's actually acidic enough to deprotonate with a strong base like sodium amide, which you can then make the acetylide ion. And then this can act as a nucleophile to displace a leaving group, to do substitution chemistry on. So you could then, have something like this, and this does an SN2 type substitution to make another alkyne. And then you can do whatever alkyne chemistry you need to do with that. So you can reduce it to an alkene and then do alkene chemistry, right? So we could go like this and then do whatever we want to do from that. We could also just reduce it completely using hydrogen, something like that. So you can look those up back in chapter 5 for more details. But those are possible ways to add carbon. There's some caveats to that. We have to be careful and watch this thing here is itself a strong base. So yes, it does SN2 chemistry pretty well, like especially with primary carbons. But when you get to a more hindered substrate, you're going to get elimination instead. Right, so if you have something like, well, here, let's go the other way. I don't know and if this works or not. I'd have to look it up, but my guess is that something like in a ring, if you try to treat that with acetylide ion, then you're going to get this more than what you want, more than the substitution, just because that's a fairly sterically hindered substrate. So if you imagine this strong base, big carbon thing coming in and trying to displace that bromine, chances are it's just going to pull off one of these hydrogens instead. but I would have to look that up to be sure. So generally, this works better with primary substrates. Okay. And Stephen asks about how to differentiate between SN1, SN2, E1, E2. Can we do that next, or do you mean in the context of this? Sorry, I was in the way there. In general. Okay, so we'll do that. We'll do that next. We'll talk about that whole thing. All right. Let's look then at the second way of adding, or a second way of adding carbon-carbon bonds, which is on aromatic rings. So if we're looking at connecting things to benzene, we have basically two choices. We have Friedel-Crafts acylation, Friedel-Crafts alkylation. So we can use acyl chlorides with aluminum trichloride to do that. We can also do it with alkyl groups, but we have to be a little bit careful with groups. There's a little bit more limit there. You can look that up again in chapter 9, 10, 9. I don't remember. The aromatics chapter 9, I think. The alkylation is a little bit harder to do. It's a little bit less reactive. So you really have to have activating groups on the benzene, like an amine, like aniline here. And you have to have, you can't really do this with primary alkyl chlorides. It really has to be ideally a tertiary or a secondary connection to work. So that's how we can add to benzene in that way. And then the last one, and maybe the most useful that we just talked about last Wednesday, is Grignard reagents, where we use magnesium to make a really strong carbon nucleophile. And this one's so useful because you can really make it from any alkyl halide, which so instead of having these very specific things you have to make the nucleophile from, like a triple bond, you can use anything. You can use anything. So you can pick some whatever thing you want to add, treat it with magnesium in diethyl ether, and make your Grignard reagent, which looks like that, which you can then use to react with all different kinds of ketones and aldehydes to make alcohols. And then you kind of have to work these up. So, So you can kind of make this whole big complicated thing here. The thing to watch with the Grignard reagents is they can add to ketones, aldehydes. You can use epoxides with Grignard reactions, but not regular old substitution with alkyl halides, because they'll just do eliminations. They're too strong of bases. So you can use these kinds of electrophiles, ketones, aldehydes, epoxides, but not SN1s, SN2s. But a very useful reaction. So if you had a chance to look, I know we just kind of did that right at the end, so you kind of were right into finals mode and not necessarily going through homework and stuff. But if you can get into chapter 12 and look through that Grignard section, do some of those practice problems, it's really going to help you with the final. There are problems that there are a couple questions that require Grignard reagents, but there's a couple that it will be helpful to use those also. So those are all the ways that we've talked about this semester making carbon-carbon bonds, I believe. Any questions about those before we move on to SN1, SN2, E1, and E2? Okay, I'll take that as a no more questions at this time. So let's look at, actually, let me pull up the notes so we can have a starting point there. And I can kind of show you where to look for this too. So if you look in, I believe that was chapter 7. Where we started talking about that stuff. You know, first we really kind of went through these things. All right. So maybe where do we go for all of them together here? That was really just SN1, SN2. Where did we go when we put it all together? Here it is. All right. How's the internet today? Can you see that? Can you read that, or is it coming through really blurry? It's good? Okay, great. So so here's really the key to that, and it's a lot of stuff, but let's go through it and find the keys. So first, you can kind of take a look at the fact that the leftmost column deals with the type of the substrate, methyl, primary, secondary, or tertiary. And really, realistically, we mostly deal with these last three, primary, secondary, tertiary. So that's definitely always the first place you want to look, because that will narrow it down first and let you know what's going on. So for example, if we have a primary substrate, we can just immediately discount SN1 and E1 because primary cations are not going to be formed in solution. They're not stable enough. So we can just say, all right, not an issue with primary cations. So then let's look at just, if we have a primary carbocation and we can totally discount SN1, E1, then we can look between SN2 and E2. And generally, SN2 is going to be the main reaction with good nucleophiles and weak bases, and with less hindered strong bases like these. In fact, it's actually sort of difficult to do elimination on a primary carbon because substitution, SN2 substitution, is really favored. So maybe we can put like a little highlight around here that SN2 is going to be highly favored in primary substrates almost always, except with really strong bases, really strong bulky bases, big things like potassium tert-butoxide. So two things we want to learn from that. One is if you're trying to figure out the product, that's helpful because you know SN2 is favored unless you see these strong bulky bases. Secondly, when you're setting up your synthesis plans, like the last part of the exam, you need to have this in mind. So do you want to do an elimination or do you want to do a substitution? If you want to do an elimination, better be a strong, bulky base. If you want to do a substitution, you can pretty much use whatever you want. All right. So then let's go to the other extreme. If we look at tertiary substrates, we can completely discount SN2 reactions. That substrate is too bulky, and a nucleophile cannot get in there to do SN2 chemistry. So we can completely discount that and just talk about E2 or SN1, E1, And again, we're looking for strong bases. So any kind of strong bases, we're going to expect E2. Any kind of poor nucleophiles, weak bases, even stronger nucleophiles are going to go SN1E1. Notice also in this table, SN1E1 always go together. You can't really separate those. So synthetically, like when you're trying to do a reaction, SN1E1 is a really bad way to go because you're always going to get a mixture of products. That's usually something you want to avoid. You want to make sure it isn't happening rather than something that you plan for and try to do. So then in a secondary situation, that's where it gets kind of messy and you can kind of have everything. So look here and see that it's again going to depend on the nucleophile as well as the solvent. So nucleophiles that are weak bases, like I-, acetate, things like sulfide bases, are going to favor SN2. Things with somewhat stronger bases, like oxide bases, are going to favor E2. Weak nucleophiles and polar protic solvents, like water, methanol, ethanol, that's going to be SN1E1. Now, this would be a whole lot of stuff to keep in your head and go through and whatever. You have the advantage of having an offline final this year. So the key for you is going to be when you see questions that could potentially deal with SN1, SN2, E1, E2, so reactions of haloalkanes or alkyl halides, when you see those, make sure you go back to the section, back to this table, back to chapter 7, back to these notes, back to this video, and think through it before just writing down whatever first comes to mind. Think about what is the nucleophile, what is the substrate, what is the solvent, and give yourself some time to actually go through and think about that. You're welcome to use the table from the book, to use the notes, and to try to make those decisions this way. And I would say do that instead of just like putting down a guess and moving on. So do you have more specific questions about that? Either Stephen or anybody, SN2, SN1, E2, E1 comparisons? I should say the other place this comes up, by the way, is in chapter, the next chapter, chapter 8, with the alcohol reactions, because you have dehydration and you have substitution of alcohols with like HBr, HCl, and those can proceed by any of these four mechanisms, depending on what the conditions are, like what the substrate is. So I believe the asks something like that somewhere. A couple places maybe. Yeah, like in number 4 here, in page 4, you've got some alcohol mechanisms to contend with. So make sure you are taking at those reactions and thinking about, okay, is this going to go SN1, E1, E2? Sorry, down here for these ones in number 4. So this one here, the bromine one. Okay. So let's see. You're confused on this one. Don't know how to do it if it doesn't have the extra substituents attached, but I don't know what to do with them there. Not sure if I remove those or where the BR. So it sounds like you have a sense of what this reaction is. We can find that from the functional group, so we can see that, for instance, there is bromine is going to be our reagent, and we have an alkene here. So we're looking at an alkene reaction with bromine. So I would go back to the mechanism, since this is a mechanism problem anyway. Go to the book where you can find a related mechanism and see if you can think about what's going on. And I think your question's a good one because it's easy to exactly follow an example from the book. When things get changed up a little bit, when the molecule changes a little bit, sometimes we get distracted and think, oh, well, what's going on now? What's going to happen now? And the answer is it depends, but maybe nothing, because you have to think about what is that reaction, what is that reagent reacting with? What is the functional group that does the thing? And how does it go through and do the thing? And if it doesn't require other pieces of the molecule to react with, then you can essentially ignore them. So you can think about what's happening with that molecule and try not to get distracted by other stuff on there that may not affect the actual mechanism. I don't know how to give you any more information without just telling you the answer. But take a look at related examples. So look in the book at some of the mechanisms in that chapter and some related mechanisms. Look at some of the homework problems that had related mechanisms. Look at some of the look at your quizzes that have related mechanisms, and see if you can put those together. I think you'll be able to find some things that are pretty similar. All right. What do we got next? Oops, wrong way. 3A, the first one. Yeah. Which of them are aromatic and which of them are not aromatic? So is that first one, so what's the issue with, you mean this one here? What's the issue with that first one? That one is weird. So what's weird about it?
So, like right in the middle of the two benzene rings, that like double bond, do I count it for both of the benzene rings? Do I count like the pi bonds on all of it? Like, do I count that one twice? Not sure where to start with it.
Um, yeah, so I would take a look at it for any of these. I would look at the electron count altogether. So you have to assume that the pi system is coordinated or conjugated throughout the entire molecule. And so I would look at it all together that way, rather than trying to um, evaluate each individual ring. Does that make sense?
No, because I thought in the notes from Monday, you had told us to take a look at the individual rings and then figure out if any of them are not.
For a polycyclic structure, well, let's see. Let's see if I can put it without crashing the computer. Let's see. I went too far. Hmm. So I'm noticing in this book, which I think is a change from a previous edition, they don't really talk about how to evaluate this, because there are a couple ways to do it. All right, so here's how I might think about something like this. So we've got in an aromatic polycyclic system, one of the things that you want to look at is if you can still draw those resonance forms going all the way around. So if we, like on benzene, we can draw everything kind of flipping, and that helps us to decide that it's actually all shared around. So let's see if we can do something similar here. Oops, not there. So do you see here that we're kind of getting stuck? We're passing this around. We can move this one up here. And then we kind of get stuck. There's no way to keep moving these things. So if I try to kind of draw the results of that, so I'm moving that one here, this one over here, this one there, and then I move this one up here. Well, that can't be right because now I've got this like extra thing um, that's not working. Let's see if we can move it in another way. So if we like kind of start over here, that looks weird. Let's do it this way. We move that up there, move that over there, move that over there, that one there. Once again, we're getting stuck here because we got here, here, then we move that one down there, and this one over here. And now, no matter where we move this one, it's going to bump into something else. Right? Because if we move over to there, and we move this one over to there, then we're in trouble because we got too many bonds on that carbon. So there's just no way to draw that resonance here. So what that tells us is that this double bond here is actually not part of that aromatic system. It's not part of that resonance going around the ring because we get stuck. It's in its own environment that way, as opposed to something like phenanthrene over here, which does actually um, work out quite nicely resonance-wise.
So it
Except I
can't be
just did it
like
wrong.
partially
But yeah.
aromatic.
What?
So I guess I'm confused still with that first one because I knew that um, the cyclopentene was not aromatic.
Hmm.
The rest of it is. So, and then you just said that it's not part of the aromatic system. So then would the whole thing not be it or partially, I guess?
Well, there is no partial answer here, so I don't want to just straight out tell you, but like you could probably figure it out. If it doesn't work out with the, then it's not aromatic. So you have to make a yes or no choice for each of these, and if something is not working, um, does that make sense? So Nicole says that you saw that it could still work as aromatic. So how or where? I could be wrong on this too, by the way. I'm looking at something else. All right. So you thought because of Huckel's rule of aromaticity, because it has 12 pi electrons, but 12 pi electrons is not. Um, Let me see what I can find. Maybe something else is going on here. So I found this. Yeah, be careful what you're finding on websites, just because they're, especially if they're like websites where people are asking questions clearly related to homework and stuff, because people just answer those and they're often wrong. If you're going to look for information online, make sure it's actual scientific information. Like, for example, I found this paper where they actually try to calculate the aromaticity of ace-naphthalene derivatives. Um, so, yeah, so yeah, it depends on the site. And it looks like doing all of this stuff, the key sentence here is here. All these methods agree that the extent of aromaticity of the five-membered ring in the ace-naphthalene molecule is quite small. So that's what we just said, really, was that it doesn't quite work. Um, it's not truly fully aromatic for the entire molecule, but it probably is fair to say that um, that like most things in chemistry, it's just not as clear as maybe we want it to be. So that's my fault for not writing a better question and not looking that up beforehand. Sorry, I was tired. But we can say that this part of the molecule has some aromatic character. This part does not. And that's kind of what we were looking at with the resonance and the electron counts too. That you can look at the naphthalene and then kind of say that that part is more aromatic, whereas the five-member ring part, probably not. So I guess that kind of answers your question, but probably not in the way that you wanted. I'll have to just sort of give everybody credit for that one, if for this particular one, no matter what you pick, because obviously it's much more vague than I thought writing a question. But thank you for bringing that up. If you do find references for this stuff, you know, like real experimental references for something, I'm always happy to look at that. So I will, as I grade these and get it back to you, you know, if you had a source for something and you got marked wrong, send me that source so we can look at it, because maybe there is something wrong there and I want to take a look at that and change it. Make sure that the source is a legitimate scientific source and not just like, you know, who answers or whatever. But if you have a source, then you should get credit for something that you found. All right, so other questions? Oh, good question. So monobromination just means adding one bromine. So if we add one bromine, how many different possible products? How many different products are possible? And when we say possible, um, well, yeah, how many different products can you make? Yeah. Has anybody gotten to start on these yet? Oh, Monday. So I'll be here, and if you have questions, you can talk about whatever. Yeah. Yeah, good. Bring your questions as you go. Oh, also, the grading policy thing from Harper College, you've probably gotten some notes about it. But just as a reminder, the way that it's working, there's no F grades this semester. They're all going to be NP, which does not affect your GPA. If you get an A, B, or C, you can elect to switch that to a P for pass, where you get credit for the class but not have the grade show up on your GPA. You don't get to make that choice until May 29th. Because all the stuff, they're kind of extending a bunch of deadlines. So there's going to be a 2-week period, May 29th to whatever's 2 weeks after that, June 12th or something, where you're going to see, you'll get a note from the school via email. You'll see both of your GPAs with and without converting your grade. And within that 2-week period, you have to make the decision whether you want to convert it to a passing grade, to a P for pass or not. Before you do that, please check with whatever programs you're applying to, whether it's like a nursing program or some other transfer program, to make sure that they don't require that grade to be reported. So if you plan on, if you do nothing, you just get your grade as usual. If you elect to, you can convert it to a P for pass if you don't want it to affect your GPA. There will be a 2-week period to do that, starting, I'm pretty sure it's May 29th. Yeah, reaction example of Grignard's again. That's where you're stuck. Let me show you the reference again in the book, and then we'll do an example also. Okay, let's use the. So we're going down into chapter 12. All right, so page like 402, 403 here. We've got how to form them. Let's get into some reaction examples. So one of the keys here is like taking a look at a product and thinking about how it's been formed from a Grignard reaction, which is what we did this one, I believe, in class. So let's do another one. Let's think about all the different possible Grignard ways that we could synthesize this, because there's often at least 2 choices. So like, let's take a look at this one, C here. All right, so here's our target. And let's see if we can find 2 different ways to synthesize this from Grignard reagents. So take a second, see if you can do this, and then we'll look at it. While you're doing that, one thing we can think about with Grignard reagents is they generally form this kind of a thing. So you've got a carbonyl that has whatever attached to it. Call that R1 and R2. And then you've got the Grignard, which is a third thing. And when those react together, the R from the Grignard is going to attach to the C. The O becomes the OH, and so we end up with this type of a product. So R3 becomes attached to the carbon, and the OH goes there. So let's think of some different ways, and actually, if you want to be really tricky, there's a really cool third way you could do this too. But let's see what we can find. There's 2 obvious ones, and then 1 less obvious one. Actually, 2 more or less obvious ones. What do you mean not the MGBR? Yes, right. The MgBr. So one of the byproducts here is just regular old magnesium bromide. I know the stoichiometry doesn't work there, but that's a byproduct. I think sometimes it's magnesium hydroxide too. Does it say in here? Yeah. It doesn't really say. There's some various products. There's definitely magnesium hydroxide, probably magnesium bromide too. So some various byproducts that happen there. About those. We're just going to focus on the inorganic parts. But one of the things that's tricky about these as you're working on this is that any of these could come from wherever. So like when you're thinking about a synthesis problem, or just any reaction where you want to make a thing or figure out what thing was made or what it was made from, you can either think about starting with the bromide that you then turn into the nucleophile and react with some other ketone or aldehyde, or maybe this is your starting part of the synthesis and you're reacting it with this as a reagent. So either way can work. You're just going to be mixing these things together. Sometimes it can be tricky to decide what you're going to start with and what you're adding as a reagent. So have you come up with any of these yet? Keep trying, see if you can find them. What do you think? You got it? You got some? All right, silence in the chat. Let's take a look. So whenever you see like a tertiary alcohol like this, or secondary alcohol, um, we can think about making it from Grignard reagents. by disconnecting various places. All right, so we can go look at all the carbon-carbon bonds that are happening around that carbon that's connected to the alcohol, and those are all possible ways that this could be disconnected, that this could be put together. All right, so first, let's look at this one on the left. That's probably the most obvious. So if we disconnect there, or if we imagine making that connection, that means that we're going to use this kind of Grignard reagent. And we're going to react it with, I'll try to keep the same orientation, this kind of a ketone. So cyclohexanone and this Grignard, that connects there. And so that makes a carbon-carbon bond between these two rings. See that? Okay. So these other two are a little bit trickier because they're happening within the same molecule. So let's do these in a couple of steps. If we break like this top one here, let's just draw it broken so we can see it and think about what that means. So we're breaking this bond, which means that this was the Grignard. And this was the ketone. And that looks kind of weird. We can maybe stretch this out a little bit so that it looks a little bit more like how we would draw a molecule. But that would actually be our Grignard. And you can do this actually to good effect because it's happening in the same molecule. There's some entropy gains, or entropy favors that sometimes. So you can take like a bromide, an alkyl bromide like this, just add it to magnesium, and you don't even really need any other steps. You just take this one molecule, and it curls around and reacts with itself to form the six-membered ring. And the third one, down here, same idea. So we're breaking that bond there. The Grignard was, whoops, not here. Hold on. I did this wrong. Missing a carbon, sorry. Because we gotta have that carbon there, right? Gotta have 6 carbons. Sorry, I miscounted that. So here, 1, 2, 3, 4, 5, 6. And then the ketone would be here. So if you have a tertiary alcohol, there's always 3 different possible Grignard reagents you could use. If you have a secondary alcohol, there's 2 different ways you could do that. Let's look back. So these intramolecular ones are kind of fun, but let's look back to this first one. The other thing to think about here is, like, let's say this is some synthesis problem. We want to make this from these 2 reagents and say, all right, which one works best? Like, let's say, yeah. So the question is, if you start with a ketone, are you always ending with an OH? Yes. You're always going to, it's a type of a reduction, really. So you're reducing the carbonyl to an alcohol. Aldehyde also. Let's say like this was your synthesis problem. And it said, start from this and make this. So we first look at this and say, oh, this looks like a thing for a Grignard reagent because it's got this OH with, and we clearly have to make some carbon-carbon bonds. So let's say we break this one, and these are the 2 parts. It's always useful to draw those 2 pieces before you decide which way you're going to go with the synthesis. Then we can look at these two pieces and say, which one brings me back to my starting material faster? And the answer here is this one. The MGBR brings us right back here directly. We can make that Grignard right away. Be the reagent that we add in the next step. Let's try a different one. So let's say if instead of that, sorry, erase that part. Let's say if instead of that, the problem was start with cyclohexanol and go to there. So then you might, like, if you're just looking at these, this is really hard because there is no reaction that just connects a thing to next to an alcohol. But if we again analyze it backwards and say, well, this could be a Grignard type connection. Now we've got these two things to choose from, and now it becomes more clear that this could go to this by oxidation, right? We could use a chromium oxidation to make the ketone, and then we could add this as a reagent to make this product. So depending on what we're starting with, if we work backwards and we analyze what are the different possible ways we could make this connection, then we have a better chance of getting back to the right place. Erase this stuff just because it's muddying up the notes here. All right, so that is 10:30. I am happy to stick around if you have more questions. So go ahead. Otherwise, I'll be here again. I'll be here Friday at 11. I'll be here next Monday at 9:30. And that'll be pretty much it. If you have other questions other times, please email me and I'd be happy to meet with you other times than those also. I know some of you really can't make these morning times. We can do evenings, we can do whatever works. So, thanks. Happy examining. See you then. All right, let's look at 1B. Okay. Well, I think you're missing something there. Uh, think about maybe the O, but I would say think about what's changing in this reaction. Those things that you talked about, PCC, hydrogen, palladium, those are functional group interconversions, right? Like you could turn an OH into you could oxidize it and make it a ketone or an aldehyde. You could reduce a double bond with palladium. You can reduce a ketone with that too, but there's another change that's happening here too that you're not seeing. So think about like just in a very simple, basic way, what changes between the starting material and the product. Yes, exactly. There's more carbon added. So that tells you that you need to look at carbon-carbon bond forming reactions. Other questions? Go ahead.
All right. Professor Rector,
Yeah,
can we have the appointment now?
sure.
Okay, cool. Actually, just three questions. The first question is I send you the research paper. The research paper I sent it to you.
Let me see.
Yeah, through Gmail.
Let me get this off the screen.